Okay. Let me share the. So, okay, so let's see what we have been discussing. We have been talking about trees. So whenever you define an ADT, an abstract data type, so you would like to have uh, a structure which has got functions basically. So let's say this the structure is called tree. I will call it as a class tree. Or you can also call it as with capital letters. The reference for today's class is chapter number, which one? Chapter number 3 of the textbook, Data Structures and Algorithms. I hope. Chapter 3. This is the reference. So how we, so today we'll talk in terms of more abstract, means not just confining ourselves to Python, although I'm using the syntax for Python, but these concepts are abstract. So when we define a class, we define some functions here, and the functions, okay, in the beginning, I need not implement them straight away. I may just define them, or I may just say, this is my function, and what does it do? So let's say there is a tree, let's say any general tree, right? So given a node n, this function will return, given a node n, it will return the leftmost child. So it returns another node, which is the leftmost child of this node. So basically, if I pass this node, let us number them 0, 1, 2, something. So when I pass 1 into this function, it will return me 3. Right? The node 1 returns node 3. And then there could be another function called right sibling. It's again a function of node, and it returns a node. So what will it do? If I pass 3, it will return 4, right? The sibling, the right sibling. And if it is an n-ary tree, let's say I have got 5, 6, 7, 8, etc. So if I say right node of 7, then it will return 8. If I say right node of 8, it will return none, right? Because there is no right node, even if there may be other nodes here. So, but this will return none because this is not the sibling. 10 is not a sibling of 8. Okay. And instead of these two functions, I may have a function called simply get children. Get children. Now, how you implement these functions, that is a different thing, means depending on your language, etc. But this is generally I'm defining get children. If I say now n, it will return a list of nodes. It will return all the children. Let's say if I pass 1, it will return 3 and 4. If I pass 2, it will return 5, 6, 7, 8. Right? This is another way to access the children of a node. This is one way, this is another way. Like these two ways go together, and this is one way. Then you may also define a function, let's say called a label of a node. This returns some string, or let's say if whatever data is present on the tree. let's say here, these are the integers which are present at each node. It will return the integer, right? If I pass label 1, then it will return 13, right? So let's say if this is 1, then this will be 13. Okay. So in this way, you can create the functions. You need not implement them straight away, but you can just define your ADT in this way. Is that clear? Is that clear?
Yes, sir.
Yes, yes.
Okay. And now when you are defining an algorithm, then you can just use these. For example, if I ask you, can you define a function for pre-order traversal of this tree, right? Pre-order traversal of this tree. Then you have to use these functions only to implement that pre-order traversal. So you will define a function called pre-order node n. You can also say node n comma tree t, but in our case, mostly from the node itself, the other things are accessible. But anyways, so pre-order n. So how do you define? How do you define this algorithm? So you have to use only these functions. So what do you do in pre-order traversal? And you can use, this is pre-order traversal with recursion. With recursion. How do you define pre-order traversal with recursion? So if you remember, you will be visiting, let's say, in pre-order, you'll be doing this node and then the child node, right? What is the pre-order traversal of this? Just a recap. Pre-order traversal of this tree will be, just tell me the indices.
0.
Then pre-order of 1.
1.
Followed by pre-order of 2. Followed by pre-order of 9.
9.
And what is pre-order of 1?
1, 3, 4.
1, 3, 4. So basically this thing will expand into 1, 3, 4. This thing will expand into 5, 6, 7, 8.
2, 5, 6, 7, 8.
Okay, got it. 2, 5, 6, 7, 8. And then
9, 8, 10, 11, 12.
9, 8, 10, 11, 12.
9, oh, this is, okay, 8 is 9, 10, 11, 12. 9, 10, 11, 12. Okay, so in this way, you do pre-order traversal. Now, how will you do pre-order traversal with recursion using these functions only? So you will say, first the node n, right? This is your node n. First you do whatever operations you want. Let's say I'm just printing the label. So you will say print the label of n. So you will say t dot label comma n, right? Because t is the tree which has this function label. Oh, sorry, it's in the brackets, right? Whatever operation you want to do at this node, you are doing, whether it is search or printing, etc. And then you will go to the first child node, second child node, etc. Right? So how do you implement it using these functions, leftmost child and right sibling? You will say, let me take a node called current node C, and which is the t dot leftmost child of the node n. right? And this is your current node. And then you have to check whether this is none or not, right? It is possible that C becomes none. So you will say if C is not none, then do the pre-order of. If C is not none, then what you do? You do pre-order of, basically T dot pre-order of, no, sorry, pre-order of comma T, because pre-order is not a function inside the class. Pre-order of n comma T, sorry, C comma T, right? And then then you will say, what will you do next? Okay, you did the pre-order of the first child node, the leftmost child node. Then you have to go to the right sibling. Until when? Until it becomes none, right? So you will say C is equal to right sibling of, or T dot right sibling. Sorry, C. No, it's correct. N only. No, right sibling of C, right? C is the child. Right sibling of C. Right? So will this algorithm work? So it will first print my current node at the node N. Then I start from the leftmost child. If C is none, I'll do a pre-order of C. Then I have to go to the next child, but this will not loop. So I have to put a loop here. So until when I have to put the loop? Until my C becomes none, right? So instead of if, I will put while here. While C is not none, you keep doing pre-order of each and every sibling, each of every right sibling in order, in the correct order, right? Is this algorithm clear? So see, we are using only the functions which we have defined in this abstract data type. How we implement these functions, we will consider later. Right? Is this clear?
Yes, sir.
Okay. So now let's say if you don't have these two functions given to you, but only this function get children is available, how will you change this code? How will you change this code if only if leftmost child and right sibling are not given? I mean, these functions don't exist in the tree, but the get children function exists. How will you modify this code?
Sir, first we will access all the children nodes, and then we will loop through all those nodes for the pre-order.
Yeah.
Traversal.
So basically only this part will change. So in this part, you will simply say for C in get children, because get children returns the list. Of the node N, and here you will do pre-order of C comma T. That's it, right? So this is the pre-order traversal of the whole tree, right? And depending on what functions are available, you will implement it in that way. Is that clear? Okay, now I would like to discuss another algorithm for pre-order traversal. It's called pre-order without recursion. Without recursion. Now, you are asked not to use recursion, but to use, you can use any other data structure. So what will you do? If you remember our discussion, recursion is similar to what? Recursion uses what in the background?
A stack.
Yes, recursion uses a stack. So if you don't want to use recursion, you will construct a stack yourself, right? So basically, you will use a stack, and let's define the stack. So let's say this stack is available to you. This is an abstract data type stack, and it has got functions. What are the functions available in stack?
Push, pop,
Push, pop,
and peek.
and another function I'm defining is empty. It returns basically true or false. It returns a boolean, right? Is empty, whether this stack is empty or not. If it is empty, then if you do pop, then it will give an error, right? So instead of that, we will just say is empty. Okay. Or you can, if your pop can return none, that's also all right. But anyways, I'm just defining it. Okay, how will I use this stack for pre-order traversal without recursion? So let's start with this. I will say my function define pre-order on the node n from the tree P. So this node n will be basically your root node, right? When you start. Okay, how will you do it now? So what will you do? So let's create a dummy tree. I'm just using indices 0, 1, 2, etc. Or don't put circles also. Let's say 1, 0, 1, 2. Okay, just a dummy tree. How will you do the pre-order traversal without recursion? So basically you will construct a stack here. Let's say a stack is S. And so what I will do, first of all, I will initialize my stack. And then I will start from the root node. Since it is pre-order, I will first process this node, right? So process this node means I will print n, whatever there. Print n means print label on n. Then what I will do, I will push this onto the stack, right? Push this node onto the stack, 0. And then I will go to the leftmost child. And when I'm here at the leftmost child, then again I will print the value here and push this on the stack. Then I will go to the leftmost child. I will take this node, process it. So it's printing the 0, 1, 3, process it. Then I will go to the leftmost child by putting it into the stack. But there is no leftmost child. So this means I'm done over here, right? I'm done. There is no child here. No more child node. So this is done. Now let's pull out the 1 from stack. Now I am again here at 1. So what will I do? I'll go to the next child now. So earlier I had gone to the first child. Now I go to the next child. Now I'm at the 4. So again at 4, I will print the 4. Oh, I will push back 1 again into the stack. Okay, I think I'm just telling. Push back 1 and then process 4. So you will print 4. Right? And then you will, this is done. Now this is done. Now again, you pop the 1. So again, your 1 is again popped out. Here now, there are no further children, so this is over. Then again pop the whatever on the stack, so basically 0. You pop 0, right? In this way, the algorithm proceeds. Now we have to write the algorithm using the functions available to us. So let's write like this. First, define the stack. Okay, now this function is not recursive. So, which means I will not be calling pre-order again. So I can define the stack inside this function itself, right? If it were a recursive function, then I would not define my stack inside the function, right? I would have defined it outside. But since this is not recursive, I can define my stack inside also. Stack, just a stack, empty stack. Then let's start from the node n. So what I will do is I will make my current node as n. And then I will.
Sir, since this function is not recursive, do we need to give in here? Only calling it on tree will be enough.
Yeah, you're right. But okay, n is just saying that I'm starting from the node n. Okay, yeah, you are right that if you want to start from root always, then you need not give this. You can simply say c is equal to t dot root. Okay, now I have to define another function in the tree, right? I need to define a function here, root, which will return the root node, right? It returns the root node. Okay, so t dot root. Okay, now what I will do is I will say I will have to define a loop, right? So just define a loop like this, and I know what is the terminating condition. When will the loop terminate finally? When my stack is empty, right? Okay, but now since in the beginning itself my stack is empty, so I cannot say while the stack is empty, because stack is already empty, unless you can push C onto the stack, and then you can use this condition. So what I will say, if my, okay, first of all, okay, let's start from here. Print the value of C, right? Label at C. T dot label at the current node, right? And then I have to go to the next child and put this node on the stack. Okay, so let's do that. So stack dot push the current node, right? And I will update my current node to the leftmost child. Tree dot leftmost child of C, right? So now from here, I have come to the leftmost child, 1, and I have put 0 onto the stack, right? And now again, when I finish this, I will again go to this one. I will process C, again push this C, and means 1 is also pushed onto the stack now, and I come to 3. Now the C points to 3. Then again, while true, I will again print the value of 3, and I'll push 3 on the node, on the stack, and I will go to the leftmost child, which is none in this case. Now, if C becomes none, then I should ideally stop. So basically, then I have to do something else, right? If C is none, what should I do? I will, this program has ended, I have to pop, right? So I have to add a condition here. If C is not none, then you do this. But if C is none, then you have to pop out the value of C is equal to stack dot pop. And so C, when you came to the, when you have popped out the value of on the stack, which was 3, actually, okay, this proceeds in slightly different way. You are, so when you are at 3, you will push 3 also onto the stack, and And then you go to the child was none. So now you are at 3. Now you apply the function right child, right? Because that is available, right sibling, that is available to you. So now when you have popped out C, you will say C is equal to 3 dot right sibling of C. Right? So you pop out the right sibling of C and you get 4. Then you process 4, right? You will print 4, put 4 onto the stack, and then go to the leftmost child of 4, which happens to be none. Now C becomes none, and here when C is not none, then this is not applicable. This is applicable. C is none. So what you do, you will pop out 4 and then go to the right sibling of 4. But again the right sibling of 4 is none, right? 4 has no right sibling. So again you will go here while true. Again your C is none, so you can come here, and then you will pop out the next thing, which is 1. So now 1 is popped out. Then you will again go to the right sibling of 1, which means you go to 2 now, right? But there is no terminating condition here, right? What is the terminating condition? Terminating condition is if my S is empty, or equivalently you can say if my C is, here you can put a terminating condition. If my C is none, basically when I pop out from stack and none comes out, then again you can break. But if C is empty, then you can simply break your while loop, the infinite while loop. So this is a method to traverse in pre-order fashion without using recursion, but rather using stacks. So it's actually true in general that wherever you want to replace recursion, you can replace them with stacks, because anyways, recursion is doing stacks in the background. But here you have more control at how actually the stack is managed. Is that clear?
Yes.
Okay, now I would like to discuss another algorithm with you, which I have not discussed before, the fourth kind of traversal of a tree, which is called level order traversal. And I will again discuss it in a very general way. Okay, we have a tree here. Let me copy it. So level order traversal of a tree. So what is the level order traversal of a tree? It basically does level by level. So let's say this is the first level, the second level, this is the third level. So it will traverse level by level. It is also called breadth first search. Breadth first search, because it will go breadth wise. So you remember the depth first search, which will go depth wise, and this is breadth first search, which goes breadth wise. Okay, so what will be the outcome? You will just print 0, the first level, and second level is 1, 2, third level is 3, 4, 5, 6, etc. So this is called breadth first search or level order traversal. Now we have to define an algorithm for level order traversal. So it's a very standard thing. So I will straight away dive into the implementation. So you need a queue for this, just like you had a stack for the previous case. In this case, you can have a queue. And you will, let's define the queue. So you will say a class queue. This is the abstract data type, which has got what functions? What are the functions available here?
NQ, DQ, and peak.
NQ, DQ, and peak. And I will define another function is empty, just to tell me if my queue is empty. Okay, now using this queue, I will define the level order traversal. This is a function which takes as input node n and a tree t. And if you want to start from the root node always, then you can just pass the tree inside, and then you will say my basically the first node is the root node. Okay, so what I will do is let's discuss the algorithm first. So how I will proceed is I will create a queue. This is a queue. Now I will start from the root node. First of all, put the root node into the queue and also process the root node. So both the things. Yeah. So first put the root node into the queue, and then you take out this root node and process. So you process this node and put all its children into the queue. So number one, you. So first is pop a node. Pop means here DQ basically. DQ. DQ a node. Process the node. And then put all its children into the queue. Which means basically NQ all its children. NQ all its children. NQ all its children. So basically the children are 1 and 2. So I'll put all of them into the queue. This was removed already. This is not there. This is dequeued. But from the behind, I have added 1 and 2 in order, in the same order. Now I will again do the looping, dequeue the node. Let's say 1 has been dequeued now. Process this node, so print 1. So earlier 0 was printed, then 1 is printed. And then put all its children into the queue. So what are the children? 3 and 4. 3 and 4 are put from back. This one was gone, like dequeued. 3 and 4 are put into the queue. Then again, take out a node from the queue, so which happens to be 2. This one goes away. Now process the node, so basically print the value, and then NQ all its children. Its children are 5 and 6. So they are added to the queue. And then again, dequeue the node. This is the node. This is done. This is gone. 3, process the node, print 3. It has no children, right? So nothing happens. Again, dequeue 4, 4 comes out, and you print the 4. It has no children, and then 5 and 6, right? In this way, you do breadth first search, or the level order traversal, by using a queue. Okay, this was the dry run of the algorithm. Now let's write the algorithm in this way. First is you have to dequeue the node. First, let's define the queue, right? I have not defined the queue yet. And let's start with the root node. So let's q dot nq. I will just use like this nq. Nq what? The root node. What is that? Tree dot root. Tree dot root. Now I will start our algorithm. I will say just do this algorithm until my queue is not empty. I can define either like this, or I can define simply while true. Okay, let me define it like this. While not q dot is empty. So what I will do, these three steps: dq, process, and nq, the children. So dq, c is equal to q dot dq, and then process, which means you print the label on c, t dot label at the c current node c, and then nq the children. So first get the children, t dot get children at c, and then just nq them. Q dot nq c. That's it. This is the algorithm. This is your implementation of this algorithm where you are using the abstract data type queue. Is that clear?
Yes, sir.
Okay. And you can implement the same thing in Python exactly in the same way. There is no need to, I think I have already defined everything in Python syntax. Okay, so in this way, if we are given a tree, then we can implement various functions using the tree functions, the functions which are defined on the tree. Now I have something I want to. Okay, these are the traversal mechanisms. Now the tree, let's come to this part. These things can be implemented, this ADT can be implemented in various ways. One of the ways we have already seen, which is by using nodes, and each node will point to its children node, right? You defined a class called node. The topic is how do you implementing the tree ADT. One method you have seen that you first define a node, class node, and you have node will have left child, right child, or in general it can have a list of children, right? It will have something called a value, something, and then children equal to a list of nodes. List of nodes. And then you will, in the tree class, you just defined, in the tree class, you just defined defined it from the root node. You just said, my root node is this. My root node is this. And once you know the root node, you know how to get children, etc. And you are able to implement all the functions, right? These functions, right? So this is how we saw. But can there be some other way also to define, to represent the trees? So the answer is yes. Now see, what are the limitations of this particular implementation? Could you please tell the tree implementation which we saw, what could be the limitations of this implementation? Yes. One limitation is that, let's say you are here, 0, 3, 4. Okay. Now, if I ask you, I give you this node 2, I ask you what are the children of 2, then you can very easily tell me, right? Just you go to this particular node and you find the children. But if I ask you, what is the parent of 2? How will you tell? What is who is the parent of 2?
0, sir.
But in the given this implementation, how will you tell?
We have to start from the root and then go checking for children, like which node has 2 as the child, and then that will be the parent.
Yes, yes. So let's okay, let me first complete all the functions which are available. The functions available here are, let's say, the functions available here are get children, then what else? Get children, get label basically, etc. These functions were available. So if I ask you to define a function called find parent, let's call it as parent of a node n in the tree T, then how will you do? You have to start from the root. So your steps will be like this. And then you traverse it in one of those methods, like traverse the tree. And you have 4 methods to traverse. You can choose any one of them. Traverse the tree and check, or basically search, which node has the children n. Search when my when node dot get children contains n, right? And then when you find that node, then you return that node, otherwise you loop over it. The traversal continues basically. Return node, return that node, that is the parent node. So it's very, what is the complexity of this function? What is the complexity? It's O(n), right? Means what this n is total number of nodes. Let's say capital N, then O(n). N is the capital, N is the total number of nodes, right? It's very computationally expensive, right? Whereas if you find get children, what is the computational complexity of that? This is for parent. Whereas for getting children, if I ask you the question, or basically I define a function, define is child. So if I give you some node n comma some node parent, no, sorry, just get child or get children. This is this get children function. What is the complexity of this?
Big of 1.
Constant over 1.
Yeah, constant, because you are directly landing at that particular node and finding the children of the node directly. So it's O1. But there may be some use cases where you don't want, or where you don't want to look at the children, but you want to know the parents. And so since you want to know the parents, so you want to make this part very efficient, right? So if you need parent, you can say more frequently than get children. Then this implementation, which we had done earlier, this is very inefficient, right? Because you want to call this function more often than this function. What will you do then? This means you should not define your data structure in this way, because otherwise you'll be in trouble, a lot of computations. How will you define your data structure then? So you will be defining it in a different way. And one such way is called a parent pointer array representation. Parent pointer, basically you can say parent pointer representation. And this forms a part of a bigger kind of type, which are array representations of a tree. Array representations of a tree. So your tree is represented as an array. How does that happen? Let's say I will say my A is an array. Oh, let me first draw the tree. We have the tree drawn somewhere. Yes, this one. Let's use this one. Okay. So how do I represent this one, this tree? So what I will do is, I will say, let me put the indices first here. 0, 1. These are just the indices. These are the indices of this array. And what are the values stored? So it points to the parent. Who is the parent of 0? None. Who is the parent of 1? 0. Who is the parent of 2? 0. Who is the parent of 3? 1. Who is the parent of 4? 2. Who is the parent of 5? 2. The parent of 6? 5. Parent of 7? 5. Right? So here, now if I ask you, using this kind of an implementation, this kind of data structure, if you want to implement this function parent in the tree, how will you do? Let's say you have a tree and in this tree you have A, which is simply this array. Then how will you find the parent?
A child.
Yeah, so you simply say return, okay, let's say parent of C, self comma C, right? Because this we are defining it inside the tree, self comma C. So return self dot A C. It's simply, this is the array index, C is the array index. And but if I want to ask you, how will you define get children define get children of some C. Let's say I give 2. Get children of 2. Answer should be 4 and 5. How will you return that? How will you implement that?
We can
Look through the whole this array and see whose whose children are
Yeah.
like
So
parental
basically,
space.
yeah. Start from root, right? Root means basically A0. Basically, 0 is the root, right? Not A0, but 0 is the root. And then you will traverse the tree. It traverses the tree, and okay, here it's a linear structure, so linear traversal is very easy. And then find all nodes with parent as C, right? Okay. Right. Okay, so this how the algorithm will look like. You will say, so okay, start from the root. So okay, I will start from root. I will just put a for loop for node. Let's say, let's call it as n. C is for the current node. N is the node. C is the current node. For C in range 0, comma. Now see the, if I am saying get children of 2, get children of 2, then they cannot appear before 2, right? If I want children of 2, they cannot appear before 2. That is how I have defined the tree, right? So I, instead of starting from 0, I can directly start from n only, right? Start from n and go up till the length of A. It means the total length of this array. Yeah, actually, more specifically, I should also define a class called array, an abstract data type where it will have the values like get value or label, basically get value, and length, right? So all these functions, all these things I should define. So get value at the node n, basically. So here I should say a dot get value n, and here I should say a dot length. Anyways, so this is how I should define, and then I will implement this. So start from, instead of root, I can start from n directly, because I know the children will not be before the parent. Children cannot come before the parent in this data structure, in this implementation of the tree. Now I have to traverse. So traversal is using the for loop, and find all the nodes with parents as C. So you can say if parent of C is same as n, then now I have to pack them up into some array, because I have to return some array, no? So let me call as outval or outlist, whatever we call it, is outlist. Is you have to initialize some empty dynamic list now, right? In case it is an n-array tree where you don't know how many children can be present, and then you can make a dynamic list. Basically, it's a dynamic list, and then you will simply say outlist dot append. So let's say this array is a dynamic array. It has also a function called append. Append what? Append the C. Right. So what is the complexity of this implementation now? What this complexity of this is simply O1 for the parent. But for the children, the complexity now is O capital M, right?
Yes, sir.
Just now your pointers are reversed. Instead of pointing in downward direction, now you're pointing in upward direction. Right? 1 points to 0, 4 points to 2. So you have the same concept of singly linked list. These are all singly connected nodes or something of that sort. Then the pointers are reversed now. Okay, so this was the implementation. Now what I can ask you is, given this representation of a tree, can you implement different functions? For example, if I ask you to do pre-order traversal, or I ask you to do post-order traversal, I ask you to do level order traversal, given this structure, this data structure, I define tree in this way. Can you do all those things? Those are exercises for you. Right? How will you do level order traversal on this? How will you do pre-order traversal on this? How will you do search on this? Or can you use this representation to implement a binary search tree? Right? Can you implement a BST using this tree, this representation? So all those questions are interesting, right? Okay, but you know that some things will be more efficient than others, right? Because here you have pointers to the parent, so it may not be very efficient to do traversal from parent to child, but doing traversal from child to parent will be more efficient. But yeah, anyway, so these are the different questions which you will ask when you want to implement these functions. Okay, so that's the thing. I thought today I will discuss with you in this way some abstract data types and their implementations. Now, there is another way of representing a tree. It is called a children list. This is again from the textbook. So you can read the textbook for more details. What am I writing? This is not a function. This is children list representation of a tree. How does it look like? Let's say you have this tree. Let's say you have this tree, and you can represent it also like this. This is another way of representing or implementing the tree. Now this is a list of, this is an array basically of all the nodes. There are 0 to 7. Let me write down 0 to 3, 4, 7. Okay, and these are the headers which point to a linked list. So 0 has a child 1. So let me put 1 in the list, and 1 points to nothing because 0 will contain, 0 will point to all its children using this linked list, right? 0 points to 1 and 2 in a linked list, and 2 points to nothing because 0 has no other children. So 0 points to all its children, 1 points to all its children. The only child is 3. This has 2 points to its children, which are 4 and 5. This is 4. This is 5. And but 5, so there are no more children of 2. So 5. And 3 will point to its children, which are none. 4 has no children. 5 has children, 6 and 7. 7 has no children. Sorry, 5 has no more children. 6 has no children. Sorry, 6 has no children, and 7 has no children. This is another representation of a tree, which is very similar to what you did using that node class. Right? But this is another representation. So the class tree the tree structure, it has got a list of headers, which is basically a list, right? Self dot some list of headers. I'll call it list of headers. This basically contains all the nodes, and then values. Right, that's it. And these headers, they point to, they are basically headers of the linked list, right? They point to the linked list. This is another representation of the tree. Now, using this representation also, you can implement all the functions of the tree, right? Like given a particular node, what is the, who are the children, who is the parent? Parent is again very inefficient here, right? Because it points in the from parent to child. So finding the parent will be ON, whereas finding children will be O1. So this is another representation which has been popular. Okay, now I will discuss something about complete binary trees. So what are complete binary trees? Complete binary tree. It can be in general any n-array tree, but what is the meaning of complete? That is what we want to discuss. So these are basically very well structured trees. For example, you have a tree 0, 1, 2, 3, 4, okay, 5. This is a complete binary tree. So the definition of complete binary tree is that all the levels are completely filled except possibly the lowest level, or the lowest level, but again it is also filled from the left. So all levels are completely filled. The lowest level may be unfilled, but filled from right. Sorry, filled from left. Unfilled from right, basically. So filled from left. Right. So this is a complete binary tree. I can extend it, no problem. 6, 7, 8, 9. This is also a complete binary tree. But if you go to this tree, is this tree a complete binary tree?
No,
No.
sir.
No. Why? Because the level, let's call it as level 1. Level 1 is completely filled. Level 2 is completely filled. But level 3 is not completely filled. Level 3 is not completely filled. Level 4 is also not completely filled. So because level 3 is not completely filled, therefore we can say it is not a complete binary tree. Now, even if it were filled, still the level 4 should be filled from the left. So again, it would not have been a complete binary tree. That is the meaning of a complete binary tree. Now, we can implement a complete binary tree in a very efficient way, where traversal in both the directions, either from parent to child or from child to parent, they are both very efficient, right? And how we do that? We do that by using simply an array, a simple array. So let's say it's this complete binary tree, and I will define some self dot array A, and A is basically, so okay, let me draw the A points. A looks like this. So you have, it's just an array, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. It's just an array, and you put all the information inside this. Like whatever the values are there, you can store them here. A, B, C, F, I, N, T, P, Q, R, whatever. So all these values you can fill here. So if I ask you now, how will you implement this tree? Let's say there is a function called, how do you find the child of a particular node? We can here call all the nodes by their index number, right? Because they have indices. So the node n is basically an int, right? And I want to ask who is the child of n? Let's say, for example, 2. What are the children of 2? Children of 2 are, it's actually get children, basically. Get children. Who are the children of 2?
5 and 6.
5 and 6. Can you implement it efficiently using this?
2 raised to n plus 1 and 2.
So you will say return what?
2 raised to n
2 raised to n
plus 1 and plus 2.
plus 1, 2 raised to power n plus 2. It's a binary tree, so only 2 children are there at most. Now, let's verify it. If we are here at 4, oh no, it's 3. So when I have 3, what should be the outputs? What should be the outputs?
7 and 8.
Put it in this formula. What do you get?
It is 9 and 10.
So what is the problem? So what is the problem here?
Sir, it's not power, it's 2 into n plus 1 and 2 into n plus 2, I think.
Okay. Yeah, it's 2n plus 1 and 2n plus 2. Now you can verify. Now put 3 here, 3 to the 6 plus 1, 7, and 3 to the 6 plus 1 is 8. So this is correct now, 7 and 8. Okay, so yeah, so always when you define, just verify with some samples. This is called testing, right? So whenever you write your code, you must do testing with some known data, with known results or known cases, basically. Known results or cases. Okay, now how will you get the parents? Single parent, basically. A tree, in the tree, always there is a single parent. You cannot have multiple parents. If I give you some node, the index of the node, then how will you tell who is the parent? Yes.
If it's odd, then -1/2. If it's even, then -2/2.
So you will say return n-1 divided by 2 or n-2 divided by 2.
Yes, so whichever
Okay, and if you take a floor of this,
yeah, that will.
right, that will also work in both the
Yes.
cases. Okay, just note that here we missed something. We missed the case 4. For 4, it has only 9. There is no 10. Right? So you have to take care of that. 4 will give a problem. So basically, you have to check whether this number is less than the length of the tree. Right? Length of A. You can define a function called define length, and it returns the length of A, basically. The length of this array. So here you have to check if n plus 2n plus 1 is less than length of A, and 2n plus 2 is less than length of A, right? If it is not less, then you will be not returning it, right? Then you will return none. Right? For example, in this case, the length is 10, right? 0 to 9 means length is 10. So 2n plus 2 is 10. So you want this should be less than A, and it is not less than A, so you will not return this. You will only return 2n plus 1. And similarly, when you pass 5, it should return none. Okay. Yeah. So that's it. Now, if I give you this, if I give you that this is my implementation of a tree, and I can ask you various questions, right? I can ask you, tell me who is the right sibling of this particular node. And I can ask you, what is the depth of the tree? Or what is the depth of this particular node? Or I can ask you, what is the, or do a level order traversal of this tree. Or I can ask you, do a pre-order, post-order traversal of this tree. Or I may ask you, can you tell me, yeah, basically I can define multiple functions. Okay, now this is one thing, right? Here I have given you a data structure, but now the next level of problems will be, I give you a problem and you have to think of a data structure which will be best suitable to solve that problem, right? That will be the next level, and I hope we will be able to do it in the coming weeks. I'll give you some problems for practice, and then I ask you, oh, maybe I can give you one problem straight away. So the problem is like this. Okay, this problem, okay, but this does not use the data structure. It's like this. You are given a tree, this practice problem. The tree is like this. It's a general tree with no particular restriction. And you have to do a level order traversal. And return level-wise results. Level-wise, or print level-wise values. Basically, for this one, the output will be 0, comma 1, 2, comma 3, 4, 5 in the brackets, comma 6, 7. So if I ask you how many entries are there in the third level, you can use this to say, okay, there are 3 entries in the third level. Right? So this is one problem. This is a special kind of function which does a level order traversal and also prints the level wise values. So it's a list of lists basically. Okay, so do this practice problem and we will discuss it in the next class. And then we will go into next topics. And I will also give you some more practice problems on trees. Okay. All right. So we stop here. Do you have any questions?
Sir, I have one question regarding the assignment.
Yeah.
Sir, you asked for rendered IP by NB file. What does that mean?
So, okay, I think any questions regarding the assignments, you can ask the TAs, okay?
Okay.
They will help you and they will also disseminate the information in a uniform way. Okay, thank you. Thank you. Bye.
Thank you, sir.